Okay, everyone, thank you for joining. I think we'll go ahead and get started for the sake of time. So today's topic is Pro4D. It's a Hampson-Russell application. And what we're going to share is the utility of 4D seismic information and how important it is to reservoir management scenarios. So our reservoir expert, Sherbin Razulzadeh, he has about more than 15 years in the industry now. He's worked on projects worldwide. And he's going to share ultimately the objective is to determine change occurring in the reservoir as a result of hydrocarbon production. So with that said, I'll pass it over to him so he can get started. Over to you, Sherbin.
Thank you, Jasmine. Hello, everybody. Good afternoon, good morning, and good evening from wherever you are. I'm just going to start. This is about Hampson-Russell Pro4D time-lapse analysis software tool, which we have in Hampson-Russell. I start with some introduction about Pro4D, about 4D, then about what we can do with Pro4D. Right, in introduction, so you know that we do seismic studies and we do seismic acquisition and processing first time on the field, and we call it base, for example. Then we do the production on the field. It will affect the fluid will change, the reservoir will change. So we do another set of 3D seismic acquisitions, and we process it. We call it monitors. Could be one time, and we can repeat it after several times. And it could be many monitors. Then we find the differences between the base and monitor or monitors, and we interpret these differences on the seismic data. So this could be the 4D seismic after the finding the differences. And from these differences, we can analyze the changes and we can infer what the movement of the fluids was happening and where has the hydrocarbon been produced and where bypassed. So saying so, typical workflows for 4D studies is like that. So we do the time-lapse modeling, and it includes also 4D calibrations, which is the calibrating seismic monitors to the base, and also interpretation of these differences. So in the time-lapse modeling, we are talking about estimating the velocity and density changes due to the changes in the reservoir. Could be changes in the temperature, pressure, porosity, could be thickness of the reservoir as well. We create the synthetic seismic data, and we analyze the synthetic traces to determine changes that may occur in the seismic data. Then in the 4D calibration, we are comparing the seismic surveys recorded at various times, and we are calibrating the various time 3D seismic data sets to the base one. And from the calibrated 3D seismic volumes, we remove those spurious differences, which is not due to the production, and we keep the production changes. Then we subtract the calibrated seismic surveys in the interpretation and map the differences, or interpret the calibrated monitor 3D and the difference surveys. And we compare the seismic differences to the synthetic traces, as we did in the modeling, and to infer the changes in reservoir. It could be due to pressure, temperature, saturation, and etc. And then finally, we estimate the area and volume of these produced zones and compare to the non-production of the field. All of these steps can be done in Pro4D, and the Pro4D is part of a Hampson-Russell reservoir characterization tool. It's integrated environment. This is a GOV environment of Hampson-Russell. And you see, if you go to the processes, under the processes, we have this time lapse, which is it's shown here. And I'm just showing here the acoustic impedance inversion for one of the 4D studies. It's acoustic impedance for base. Reservoir is in this location. And this reservoir is steam assisted production is going on this oil field. And the hot steam is pushing the oil towards the wells. And this one is acoustic impedance base minus monitor. We have 3 monitors and 1 base, so 4 surveys. And this is the differences of the acoustic impedance after inversion. So you see that the production effect has been shown here. Anyway, I'm just giving you a quick example here. But the main example idea showing this is that Pro4D is under Hampson-Russell, and it can provide the tools for you for enhanced data management, well-log toolkits, fluid replacement and rock physics modeling, synthetic seismic generations, displaying, comparison, calibration, interpretation, and inversion of these multiple surveys, and to be able to find out where is the swept area and where is the remaining hydrocarbon areas. In the time-lapse modeling, if you go forward to this presentation, I will follow the same order: time-lapse modeling, calibration, and interpretation. So I start with the time-lapse modeling. In the time-lapse modeling, we can go for rock physics, and we can use rock physics models, and we can estimate different variations. And as you know, the reservoir consists of the mineral and the matrix, and also fluids. And this fluid is changing, so and the vast majority of the time-lapse changes are related to changes of the fluid properties. So what is affected by the changes of the reservoir properties? For example, we are talking about bulk modulus of the rock, and shear modulus of the rock, and the density of the rock. So these three parameters are very important in the elastic property estimations. We can estimate P velocity, S velocity, and density is there as well. So these will be affecting the seismic data and seismic velocity. So bulk modulus is affected by the rock frame bulk modulus, which is the skeleton of the rock, and itself is affected by the porosity, effective pressure, and also the fluid bulk modulus, which is also a function of the saturation, temperature, pore pressure, and mineral bulk modulus as well is affecting the bulk modulus of the rock. For the shear modulus as well, so we have the effects on the rock frame, the skeleton of the rock, which is coming from the porosity and effective pressures, and also the mineral shear modulus is also having a good effect on the shear modulus of the rock. And density, as you know, that the matrix density or the mineral density and also the fluid inside the rock is affecting the density. But this saturation, temperature, and pressure have the biggest impact on these elastic parameters. So how to model this? We can use rock physics modeling, and the rock physics modeling options are available in Hampson-Russell or in GeoSoftware. They are RockSI, which is advanced rock physics modeling tool. We can do rock physics models can be used from extensive rock physics models library within RockSI, or we can edit our own rock physics model, which is appropriate for our field. And we can use this rock physics to estimate what will happen if the saturation changes, pressure changes, temperature changes in the reservoir. I'm not going to talk about the RockSI today. I will talk about the systematic changes, which is part of fluid replacement modeling tools of the Hampson-Russell, and it will use a Biot-Gassman method to change the fluid, the saturation, and also pressure and temperature inside the reservoir, and see what will happen on the reservoir elastic properties, which is VP, VS, and density. Talking about RockSI, for example, this is showing a cross plot of acoustic impedance and the VP/VS, and this is our well-log color-coded by water saturation. And you see that this area is a reservoir with less water saturation, high hydrocarbon saturation. So I can establish my rock physics model, and I can display a rock physics template using my rock physics model with different parameters. For example, for this case, I'm showing that if the porosity changes, what should I expect from the reservoir? If the water saturation trend changes, what should I expect? So this rock physics template can help me to identify the variations. This is for the in situ condition. It could be in the next situation, which is changing in the temperature or pressure or saturation. So for example, in this case, I'm changing the temperature from the initial condition, this green ones, and to the increased temperature, this red one. The good thing in RockSI is that we can generate the examples and using the Monte Carlo simulation. And with this Monte Carlo simulation, I'm able to estimate the probability function of, for example, distribution of, for example, my reservoir in two different situations, in the initial condition, in the increased temperature condition. This can be used for next step, which is interpreting the, for example, inversion results. For example, you have acoustic impedance and VPBS from 4D, or the variation of that, you are able to interpret those using this type of calculations, this type of PDFs actually. Going to the fluid replacement modeling. So what we do in the fluid replacement modeling within the reservoir, so we have the P velocity, S velocity, density. And within the reservoir, for example, I am going to see what's the gas effect on my input data set. These blue ones are the input data sets. I'm adding some gas, and you see that the velocity is decreased, or this sonic is increased for the P velocity. S velocity will not change, but the indirect effect is that the density is changing, as you see here. Then it will have effect on the shear wave velocity. And also density should change because gas is added to the water. That's one effect. So I can analyze different effects one at a time, and with using this fluid replacement modeling. Or I can also combine, for example, changing the temperature and pressure, and see the effect of the increasing temperature and pressure in the reservoir. So you see that they have the variation as happening at the P velocity, S velocity, and the density in the reservoir. That's fine, but the thing is that I'm not able to include the overburden pressure inside this modeling, and I'm not able to see variations. So I can use systematic changes, which is a advanced tool for the fluid replacement modeling. It comes under AVO modeling, but it can be also used for modeling 4D effects. So under this one, I have options. For example, I can create a pseudo 3D. Pseudo 3D is that I am varying inline changes, x-line changes. These inline changes and x-line changes could be any variable. For example, could be porosity, pressure, temperature, or other parameters, which is shown here. I can set that. I am saying that, for example, we start from pressure changes from 0.5 megapascal to 2.5 megapascal. Every 0.5 megapascal, just show me the variations. And for temperature as well, starting from 10 degree to 250 degree, and every 20 degree, create this model of the elastic model. Then I can also add this pressure effect on the elastic properties. The pressure, usually it comes from the laboratory analysis, and you can get these relations with, for example, VP of the pressure. So you have this overburden pressure calculated here. It can use integrated density or other values. If you know, you can just put it in here. And some relations between VP, for example, the effective pressure and the VS versus effective pressure. These A-B equations you see here, they usually come from laboratory analysis on the core data sets. So it can create for me these elastic properties. Then next will be the synthetic. So in the synthetic tab, so I can just select the synthetic options, for example, the time window, and also the synthetic type. So this is the, for example, if I'm going to the zero offset or angle gather or offset gather, because this is under AVO, I can go, for example, NMO corrected, NMO stack, or plane wave uncorrected. So travel time. I can also do the other stuff like geometric spreading, VTI and anisotropy, and etc. But for this case, I am Pro4D just uses the one stack data or post stack data. So I'm just creating post stack synthetic data sets. So here with the example, so each line showing the temperature, the pressure variation. So I have 1 megapascal line here, and this is 0.5 megapascal, this is 1 megapascal, and 2.5 megapascal data set. And each trace here is calculation of the elastic properties, and after that, synthetic seismic generated using this option here, and it shows that synthetic seismic, for example, at 10 degree to 250 degree centigrade. This is my reservoir here, and at this reservoir I have oil, and you see that at the low pressure, gas is coming out of the oil, so I have less velocity here. This color is velocity, as you see, there's less velocity and high velocity. But if I see, for example, here the pressure is increased, gas is inside the oil, so the velocity is high, so that this time from top to base of the reservoir is less as I compare to this one. And you can just analyze how what you can expect if the pressure changes or if the temperature changes in the reservoir, what you can expect from the seismic data. So this synthetic seismic can be generated for you as a pseudo 3D. So Next, we need to go to survey calibrations. So we identify, for example, what I can expect from the temperature changes, pressure changes, and saturation changes in the reservoir. I have my seismic data. I need to calibrate those seismic data to the reference. So the time-lapse seismic analysis involves the comparison of the surveys recorded at various phases of the production, various phases at various times. There are many different opinions how to calibrate or condition the 4D surveys before interpretation, and many will give similar final interpretation results. The biggest difficulty is calibrating surveys, which is the removing unwanted differences while not altering the desired differences. So we don't want to remove the changes coming from the production. So we just want to remove the, for example, processing related or acquisition related differences. The thing is that we need to be careful not to do excessive calibration during the seismic processing stage, which will remove that effect and also complicate interpretation. In Pro4D, we have tools that can help us to remove these spurious differences while assessing the level of the change in the production anomalies as well. I've shown an example here. I have left-hand side base seismic data, the middle is monitor data, and the right-hand side is the color-coded with the difference of the amplitude. As you see, there are lots of variations in the amplitude here. This is my reservoir shown here. I'm expecting the differences to be shown here, or not above the reservoir, not below the reservoir. But these are not real effect from the production. So these are just because of the acquisition and processing difference. But after you see that after calibration, so those will be removed, and I can just see some variations here, which is related to production effects. So above the reservoir, I just reduced all of those differences, and below the reservoir also reduced all of those variations. As a general workflow for this conditioning or the calibrating seismic data is like that. So we have a base data, base acquisition, and we have monitors, or one monitor or different monitors. We can do first step could be just do some cross correlation of the base and monitor to find some overall correlation coefficients and shift between the monitors and base. And we can use some QCs like calculating differences, calculating cross correlation values, and to see how much is the overall shift required. The next step, we can compute and apply average phase and time shift using the phase and time shift. Again, it's correlation based. Then we apply those phase shift on the monitor data, and our monitor data will be phase shifted. Then the next will be shaping filter, and then shaping filter will shape or in a frequency, and the phase content of the monitor will be similar to the base. Then we apply that on the monitor, we will get the shape filter. Then there will be some differences between the amplitudes of the base and monitor, so we need to normalize those amplitudes. The next step will be normalizing amplitudes. And finally, after normalizing the amplitudes, we are going to find if there is any statics or time differences between the surveys and the base and the monitor surveys in the shallow parts, which is not related to reservoir. So we need to remove that. It's called X correlation or cross correlation statics. We remove this the time delays, and we will get this calibrated monitor volumes. So this calibrated volume can be interpreted in the way that to find the difference in the time. It could be time delays in the base of the reservoir. So we can interpret those, or we can try to align that time of the base of the reservoir to the reference and just interpret the amplitudes. In this case, we have two options. So we do interpret on the time delays, and we have option of interpreting the differences of the amplitudes. So amplitude differences comes from the velocity variations and acoustic impedance variations. But the time delays comes from the just velocity variations. We see those workflow, but to make it easy in Hampson-Russell, we have this the different workflows for different studies, and for 4D as well, we have this 4D calibration workflow. within that workflow, so you can easily follow that steps. And this is a predefined default workflows. You can add any steps you want or remove any steps if you don't like, and use it for your data sets. So you don't need to, worry about if I'm doing the right workflow or not. So it's already here. In the calibration process in Pro4D, so we have, if you open these processes in the Pro4D, you will see that we have a survey grading, which is for if the monitor is not the same as the size, the reference grid. So you can just regrid your monitors to the same grid of the reference seismic data or base seismic data. Other than that, we have QC tools for generating standard 4D metrics. For example, you can calculate correlation coefficients and shifts, normalize RMS differences. You can calculate predictability. These are the tools used for estimating how the two data sets or monitors are similar to the reference survey. For example, you can calculate area expansion, etc. So we have several options to calculate these metrics. In the preconditioning, for example, we have calculated correlation coefficients and time shifts, but we don't like those time shifts. They are too much, so we can do conditioning here, we smooth them, and maybe apply spatial interpolation for them, so we can do preconditioning on those metrics here. And finally, we can do the calibration, apply, for example, filter, apply RMS factors, etc. on these sections. So we have three sections in this calibration: QC, preconditioning, and calibration. Example shown here, this is shaping filter. Pro4D filter option estimates a transfer function that matches the frequency content, phase, which is a frequency dependent, time, and average power of the two datasets. Two datasets is mean monitor to base survey. It uses a Wiener-Davidson time domain filter for matching where the cross correlation of the two datasets is matched to the correlation of the autocorrelation of the reference. So cross correlation of the two datasets to the autocorrelation of the base survey. So the filter is required in between. So what will happen here, for example, this is monitor survey. After applying this shaping filter, you see that the differences, where the differences are located. Shaping filter, we have options here. For example, it could be zero phase, it could be full phase matching, or it could be combined. So if you look at this here, it is a cross correlation of the input or autocorrelation of the base, and cross correlation of input to output or monitor to base. So we want to find these two correlations should be similar. So the shaping filter should be applied on the cross correlation of the base to monitor to be same as the or similar to the autocorrelation of the reference. And if you look at the frequency domain, we have these input wavelets or input cross correlations from input and the base and monitor. Base is blue and monitor is red. So we apply this shaping filter, and you see that these output wavelets or the autocorrelation from the autocorrelation, which is blue, and the cross correlation, which is the red, is they are following the same amplitude spectrum, and also in the time as well, they are almost the same. Amplitude cross correlation. Sometimes the amplitude differences between base and monitor data can be caused by difference in seismic acquisition, data processing, or production effects. And amplitude differences caused by scaling can be corrected using the RMS factors. Again, so we calculate RMS of the monitors and RMS of the bases, and we divide them together to find the scaling factor to apply on the monitors to be similar to the original. So we have this base, this is a monitor, and if you just subtract them from each other, you see that lots of differences here, and we cannot get any production effect here. So we need to do something on this data set. So we just calculate some scales, and we apply these scales, and you see that these black ones are the scaled monitor ones. So if you just remove this minus the base one, you see that 0 in the places there is no production effect. Shallow statics, it's the places that above the reservoir. So we see some variation. This is due to the acquisition processing and maybe the differences in the acquisition and processing. So we need to remove those variations because these shallow time shifts can cause differences that mask the production effect. So we check at the shallow part. So we have a base survey here, monitor survey here, and monitor survey, which is shift applied here. You see that the shift has moved these data sets upward. So we need to remove that shallow statics or shallow time differences above the reservoir. Example shown here, this is the left one is base minus monitor color coded, and this is my reservoir. And you see that I have lots of differences between the amplitudes here. But if after applying this statics removals, you see that that part has been removed, and I don't see that much variations because of these shifts in the above reservoir. After calibrating, removing those time statics above the reservoir, and also applying shifting, phase shaping and shaping the filters, shaping the monitors to the reference. There is also some other effects remaining, and it is called the time variant time shifts. This is due to production. So we want to keep this, or if we want to do amplitude variations studies, we need to just align all the events together, and we just need to see the amplitude changes between the monitors and the references. So example here is shown. I have a reservoir here with some production effect here. At the depth, they will not change top and base of the reservoir, but in the time it will change. So this is good. We can interpret this as some production effect, this time variance between the monitor and the reservoir and the base. But if we want to go for example, inversion, we need to align these base and monitor to each other. So we need to remove that. There are different methods to remove this. For example, we have conditioned cross-correlation. It uses cross-correlation method, the Taylor series expansion method, dynamic time warping, and dynamic vector warping with Gaussian correlation. In the conditioned cross-correlation, as you see here, I have a base minus monitor shown here. And their cross-correlation, this is showing the cross-correlation, low to high cross-correlation values. And I see that time shifts, which is required to get that cross-correlation there. This is very noisy, so I don't like this. It is a very patchy. And based on my studies, for example, I am looking for some negative values rather than the positive values. So I need to remove these data sets. I can do conditioning these cross-correlation and time shift values. I can just do cross-correlation between the time shifts versus cross-correlation. And I can say that I am confident on the cross-correlation, and the time shifts are at this 100% cross-correlation value at this line, and 70% to 100%, and at this area of the time shifts. So I can apply this on the time shifts, and I can make it smoother, and I can apply this smoothed or conditioned cross-correlation on the data sets or the monitors to match them to the base. This is one way. Another way is using the Taylor series expansion. It's based on Naini et al.'s multi-vintage time shift estimation procedure that was based on earlier work by Hatchell et al., and it was on 4D geomechanics reservoir monitoring that used the Taylor expansion method. So in the Taylor expansion method, as you see, it's been applied here. It's available in Pro4D. This, if I compare to the unconditioned cross-correlation, the Taylor time shift, we don't need to do any conditioning. It will show me that smooth variation of the time shifts. Another method is dynamic time warping. That was first developed for voice recognition by Sakue and Chiba in their paper Dynamic Programming Algorithm Optimization for spoken word recognition. It was then used for stretch and squeeze speech to match the stored voice pattern in phone conversations. Again, it's talking about voice and waves. And then Dave Hale from the Colorado School of Mine adopted this algorithm for seismic processing and published this paper. In algorithm in Pro4D has been implemented, and we are using this in the Pro4D as well to time variant time shift application. So example is shown here. Again, you see that this is cross correlation time shifts without conditioning, and this is dynamic time warping shifts. So you see that it's smoother. It's a little bit different than the previous one, Taylor, but this is another way of doing this time variant time shift analysis. Another way to do this warping, that was warping in vertical directions, but could be warping in the three-dimensional. So this is called dynamic vector warping by Gaussian correlation. And Dave Hale published a paper in Geophysics, a method for estimating apparent displacement vector from time-lapse seismic image, which was proposed a way to compute all three shifts. Three means vertical, inline, and cross-line direction. This is extension to the correlation equation, which shows earlier, which I showed earlier. And the basic problem is now to find the 3D dimensional vector shift, which is in time direction, inline direction, x-line direction. Example shown here. This one is showing the time shifts from that method. And the other one is showing the inline displacement and cross-line displacement. So these why we have this displacement, because due to the production, so we are expecting that there's changing happening in the reservoir laterally as not just vertically. So this is the idea that we can calculate this type of time variant time shifts, or I can say now laterally time shifts as well, to be applied on the calibrated data sets to remove that time mismatch due to the production, because the idea is I am going to use this for amplitude variation analysis rather than time variation analysis. So comparing all these three together, so on the top I have a time slice from those time shifts starting from these are the condition, Taylor, dynamic, and 3D vector warping. So you see that for top one, all of them are showing almost similar features, but if you go to the, for example, 3D vector warping by Gaussian correlation, it shows smoother variations. Maybe that is what we are looking for. So we need to test this for our reservoir and our field to see which one is suits us better. The bottom is the amplitude variations, which is a normalized root mean square map between the base and monitor at the reservoir layer. So you see that again, it shows maybe this one is showing better correlation with the production. So we need to check this with the production at our field. Comparing them in the section view, so I have base minus monitor. These the color codes are the base minus monitor without calibration. This is after the calibration and conditioning correlation application. This is after Taylor expansion application. This is after dynamic time warping and dynamic vector warping. So you see that the details of the variations are changing. And again, this is we need to investigate which one we would like to go ahead. So we calibrated our monitors to the base, and next is to do the interpretation. Interpretation could be interpreting time delays or amplitude differences. So time delays is before time variant time shifts application, and amplitude differences is after applying time variant time shifts, which is coming to the 4D inversion as well. Example here is showing that I can do calculate the thickness or the time delay at the reservoir base and see, for example, how is the reservoir base is changing. So I have 3 monitors case here. And this is the base minus monitor of the base of the reservoir is changed. So this is the time thickness here is shown that 5 milliseconds is maximum, and I have negative or zero almost variations of the base of the reservoir. So as you see that these are the injection wells, and it was injecting at different times. So this monitor 1, monitor 3, 2, and 3 at different times has been acquired, and they show that how this injection or the gas injection was progressing at these different wells, which is also corresponding to the what was done in the field. This is one way of interpreting the fields, and it shows the gas front, and we can use that to see, for example, at this point we don't have any sweeping happening, so maybe we can drill some well here and do injection somewhere there. 4D inversion is another way. So this is the way that we do amplitude variations analysis between the monitors and the reference. So inverting time-lapse volumes can provide quantitative information regarding impedance changes. It could be acoustic or shear between the surveys. Time delays caused by velocity changes in the reservoir must be removed as part of the calibration process, as I mentioned, time value and time shifts. And the time delay information can also be used to enhance the inversion process by providing information below the seismic bandwidth, resulting in what we will call 4D inversion. So how we can use it, I will explain that time delays. But before going that, we have this model-based inversion. How does it work? Let's see how it works. We have this post-stack seismic data. We need to have this initial model to start building or changing this initial model until we have the synthetic calculated from initial model matches to the seismic data. This is just post-stack inversion. And finally, we get this final model, which has been generated through those iterative variations or changes to create synthetic to match to the seismic data. Right. But we have this time value time shifts, which is again caused by this production. So this is some area that's causing these changes. We can see that the T or the time of this thickness of the reservoir in time domain is calculated from these equations, and the D is a constant. Usually the thickness is not changing in depth. It usually changes in time. And if it's changing in depth, then we need to use another approach. This is not the approach to use for if the depth of or thickness of the reservoir is also changing. Then we can use this information to create some sort of new low frequency model. So what we do in this inversion method is calibrate surveys to remove acquisition processing related time delay differences, measure time variant time delays caused by production-induced velocity changes to align the monitors to base, apply time variant time shifts to align the base and monitor, and derive low frequency velocity information from time delay. So this time delay is very important, so we can use this to for that model generation or that initial model generation. And we can incorporate low frequency velocity information into low frequency model before inversion. So this is our initial model. That's my reservoir. This is my reservoir from here to here, and this is acoustic impedance. It's kilometers per second multiplied by grams per cc. And these are the well logs, which are acoustic impedance well logs. And this is base inversion using the same model. But you see that if I do another inversion on the monitor and calculate the differences, this area doesn't show that much clear anomaly. So it's not very clear. So the idea is to use that time delay. So I can use this time delay equations, and I can update this the initial model using this velocity scalar cube coming from this equation. And this is updated initial model. You see that there's changes here happening. And I can use this for monitor inversion. So you see that after doing this monitor inversion and after calculating the difference between the base and the monitor, I will see this nice anomaly appearing here, which is also confirming the production, what we expect from the production. And also we can also do the 3D viewing and capture the areas. So the standard inversion and the integrated inversion. So this anomaly is captured here. It doesn't show that much. Everywhere is anomalous, but here you see that it's only around this 3 wells. This is 3D, but if you see this around these 3 wells, you see that effect. Or you can calculate differences for different monitors. I have 3 monitors, and the impedance differences at the reservoir. You see that monitor 1, monitor 2, and 3. I can create these acoustic impedance differences. So this will give me some sort of quantitative measure of the acoustic impedance variations. So I can use these variations, for example, to estimate saturation changes or pressure changes by relating this acoustic impedance to the saturation and pressure changes. This can be done in the rock physics modeling part. As a conclusion, Pro4D is a program that integrates all the key elements required for time-lapse seismic monitoring, which is including enhanced data management, well-log toolkit, fluid replacement and rock physics modeling, synthetic seismic generations, and more importantly, to display, comparison, calibration, interpretation, and inversion functions for multiple time-lapse 3D surveys. All right, thank you very much. If you have any questions, please type in the box you had, and if you have the time, we can answer those.
Yes, I think we do have some time. So I have a few questions here for you, Shervin. So this first question is a 2-part question. First question, is it possible to use other rock physics models, Custer and Tokes or other methods in RockSI for fluid substitution? Second part is, are there any carbonate models in RockSI?
Yes, RockSI is, we have 3 tools for RockSI, rock physics modeling, sorry, which is coming from different disciplines. For example, one coming from the petrophysics, which is called the rock physics modeling, RPM or rock physics modeling. Another one is coming from JSON tool, which is called the Largo, and another one is originally, developed in Hamsun-Russell, which is called RockSI. So we have models there for example, for carbonates, for consolidated sand, for cemented sand, for shaly sand, for different type of models. So, and I have, we have integrated all of these models into new RockSI, which is also available inside Hamsun-Russell and other tools as well, and also as a standalone. Yes, we can use those models, which is Custer-Toksos is one of those models which is used for carbonate modeling.
Okay, great. And then let's see here. So that concludes our questions. But if there are any other questions that may come up in the next couple of days, you can contact us via these emails. So just so you know, we do have a worldwide support available in various regions, and you can visit that link to find them. Also regional contacts for other information. And if there's a certain question you'd like to ask Shervin, please feel free to send him an email. Other than that, if there is something about questions on the tools presented today, you can send an email to gs.solutions@cdg.com. Actually, I have one question come in just now. They have a question about slide 33. So let's just take a quick look if we have some time.
Sorry, I didn't hear that. It just broke.
Yeah, there's a question that came in about slide 33. So maybe we can go back to slide 33.
Oh, okay, slide 33. Okay. Let me go quickly here.
All right, if you want to go ahead, we're going to go to slide 33, and then you can ask your question.
Okay, can you hear me?
Yes.
Okay, right. My name is Jaap Mont. What I would like to ask you is that I look at differences on slide 16 and also on slide 32 or 33, yep. I would say, and I'm a bit surprised by the amount of change outside the reservoir. Isn't that a warning that something maybe has gone slightly wrong?
Yes, actually, we shouldn't expect anything outside reservoir. So we are trying to actually, if you look at this area, so this is without calibration. So we are expecting so much differences between the uncalibrated what's called 3D surveys. But after calibration, we are minimizing those variations. So it should go, ideally it should go to 0, but there is noise there, so we cannot go to the 0 outside reservoir.
Okay, so you're not too worried about the fact that you see, even after conditioning, the same amount of changes outside the reservoir than in the reservoir?
No, the target is the reservoir, so I am not concerned about the outside reservoir, but I need to do the optimum, conditioning. If I do lots of conditioning, I will also kill the, that production effect. So I don't want to kill it.
Sure, I agree. Okay, thank you.
Thank you as well.
Thank you for your question. And just scanning the question pane again, and that is our last question. All right, and like I said, we have information where you can contact us, and we hope you'll join our next webinar, which is fully leveraging the value of azimuthal seismic data, which will be next month, and then we'll close out the year with a deep learning for reservoir property prediction in December, and I'll be sure to send everybody those links. Again, we thank you for your time in joining us.
Thank you very much. Bye.